Hello everyone, here we'll be discussing confidence intervals. Particularly I'm going to be looking at confidence intervals for the population mean, and there's two scenarios. Either we know the population standard deviation or we don't, in which case we know the sample standard deviation, which is a little harder to talk about, but we'll still discuss it actually. So here first off, let's discuss what a confidence level actually is, and with that we need to discuss what is known as a significance level or a level of significance as well. So here we say a confidence level is just a ratio of certainty. So we're a certain level of confident that our answer is indeed correct, that a given statement is true. The significance level alpha is the complement of the confidence level. So if we're 95% confident, then that means our significance level is 5%. So it's how significant our confidence is basically, or how far off we are from being accurate. That's kind of how you would see it. So in other words, CL, confidence level, is 1 minus alpha, which is the level of significance. So now we go on to the statement that's very specific when it comes to estimating the population mean for a population given a certain sample. And it's this. So it says we are 1 minus alpha times 100%, so that's just our confidence level really, percent confident that the mean of a population, mu, is within this error, which is known as a margin of error, which is a z sub alpha over 2, which I'll discuss shortly, times sigma over radical n of the sample mean. So within this error of the sample mean. So this is kind of the main calculation we'll be discussing when it comes to finding an estimate for the population mean of a population. Now, one thing we need to discuss here is that in order to use this in reality, there are some requirements, and that's that the sample size be at least 30. And I want to say that the population also be normal, but in reality it's one or the other. So if it's bigger than 30, we don't need the normal requirement, but I'll just write that anyways. So let me just say population is normal. So it's kind of another requirement that we, again, don't necessarily need. In this case, it's one or the other really, but with the population being normal, it only helps. So I'm just going to write that as a certain requirement. So, and again, a lot of the problems we'll be discussing won't really have these requirements. We'll just kind of look at exercising this principle of calculating the estimate really. Now, the other thing is that, well, here, n, or not n, but sigma is the population standard deviation. And that's kind of hard to standard deviation. And that's kind of hard to calculate. In fact, you generally don't calculate this. Otherwise, if you were to calculate the population standard deviation, you would need all values of the population, and at that point, you can just calculate mu straight up. So the kind of idea here is we want to infer what the mean population is given a sample only. So this is known as inference statistics, where you're given a sample and that sample can tell you something about the population that the sample comes from. That's basically what we're trying to do. We're trying to get hints from our sample, a sample from the population, as to discuss, the certain attributes of the population. In this case, we're talking about mean. Okay. Now the next thing, what we've all been waiting for, I think, is this guy here. What does this mean exactly? So by the way, getting back to sigma, since it's hard to calculate, it's usually given for the population standard deviation. So just to be clear on that. But now as an extra note here, what does z sub alpha over 2 mean? Z sub alpha over 2 is the z value, or z score you can think of, that corresponds to a right area of alpha over 2. So z sub alpha over 2 is such that we have this image here. In fact, let me draw it in red and black so I can shade the region in red. That may be better. So we have this standard z curve. Of course, the mean is 0 in this case. And z sub alpha over 2 is this certain z value on the z-axis for this curve, such that the area to the right is alpha over 2. Now you may ask, why alpha over 2? Well, as it turns out, if you take the negative of this, you get negative z sub alpha over 2, which, by the way, according to this definition, is going to be z sub 1 minus alpha over 2, which is a little hard to understand at first, but z sub 1 minus alpha over 2 means that the area to the right of the z value is 1 minus alpha over 2, which is certainly true because the area to the left of it must be alpha over 2 because it reflects from this z value whose area to the right is alpha over 2. So that statement's a little bit of a mouthful, but that's certainly true. And notice that these two tail end regions, alpha over 2, are each half of alpha, which is indeed our significance level. So this right here, this whole area in the middle, must be our confidence level. So z sub alpha over 2 and negative z sub alpha over 2 are what is known as the critical values, and these critical values separate the middle confidence level percent from the other two tail ends, which add up to the complement of the confidence level, which is the level of significance, alpha. Whew, that was a mouthful. Now, what does that mean for us? Well, I'm glad you asked. To calculate z sub alpha over 2, there are a few ways of doing it, and long story short, we can just do this. Inverse norm of 1 plus our confidence level over 2. Or, another way of seeing this is its inverse norm of, well, if the area to the right is alpha over 2 and inverse norm takes in the area to the left, then notice the area to the left must be 1 minus that. So it's going to be 1 minus alpha over 2. So hopefully you can see why it's 1 plus the confidence level, because 1, of course, is 2 over 2. 2 over 2 minus alpha over 2 is 2 minus alpha over 2, like that. But 2 minus alpha is just 1 plus 1 minus alpha, and this 1 minus alpha is just our confidence level. So we indeed get c plus the confidence level over 2 on the inside of this inverse norm. So we'll be doing a few examples where we'll actually see this come to light, but that's going to be in this. And beyond that, beyond finding z sub alpha over 2, for the error, the margin of error, capital E, that is the error within our estimate from x bar. So x bar plus this error is our upper bound, x bar minus this error will be our lower bound. So now let's take off into some examples where we actually see this utilized. Right, so this next example I think is a pretty good example of what I just discussed, so let's see if we can figure it out. So it says a random sample of 40 kittens in a certain region are weighed, and the mean of the sample is 12 ounces. We are asked to estimate the mean weight of the entire population of kittens in this region with 95% confidence, and we are asked to assume a population standard deviation of 1.3 ounces. Now, just to jump right into this, we first need to really calculate E. So we want to calculate our margin of error, E. So now notice, we want to do this, let me write it off to the side here. E is z sub alpha over 2 times sigma over radical n. So now we really need to label things. So let me just kind of write over here a list of labelings. Z sub alpha over 2 we'll discuss at the very end, but that is known from our confidence level. So we need to find our confidence level. That'll allow us to find alpha. From there we can find alpha over 2 obviously, and so we'll discuss that afterwards. We need sigma, we need n, and we of course need x bar, which I haven't really written anywhere, and I kind of explained how it interacts with E, but we don't really know yet. Right now, let's just list these. So if we look throughout our sentence here, our random sample is of 40 kittens. So that means our sample size n is 40. Okay. By the way, the requirements I mentioned earlier, one of the requirements that I did not mention was that the sample has to technically be a random sample. But again, in all of the problems we'll be seeing, it'll be assumed that those requirements are met, even though I'm not specifying exactly what the requirements are. But if you wanted to look into it and get a little more deep into that, you can obviously research on your own. But again, all we really want to do is just have an understanding of what that formulation does for us as far as estimating the mean, given that all of the required information is given, obviously. So the sample size is 40, and we have a mean of the sample being 12 ounces. So our sample mean is going to be 12, so that's x bar, good. What else? Oh, it says use 95% confidence, so our confidence level is in decimal, 0.95. The complement of that is 0.05, because notice that's just 1 minus 0.95. Good. And this implies that alpha over 2 is in 0.025. So we can talk about z sub alpha over 2 shortly. And then the last thing is the population standard deviation, which is given to be 1.3 ounces. Perfect. So now let's get started with actually finding z sub alpha over 2. So z sub 0.025, according to the calculation I gave you earlier, is inverse norm of 1 minus this. 1 minus 0.025. 1 minus 0.025 will be 0.975, I believe. And you can use your calculator, but this will give you about 1.96. This is a pretty common number in statistics when it comes to 95% confidence level that has to do with these kind of two tails. But again, if you type this in your calculator, inverse number 0.975, then you'll get 1.96 about, if you round to two decimal places. Good. Now this wasn't the only way I showed you how to find inverse norm, or to find z using inverse norm. We could have also done 1 plus this over 2 inside of the inverse norm, but notice if you add 1 to this, you get 1.95, and if you divide 1.95 by 2, you'll indeed get 0.975. So regardless, we'll get the z value for our z sub alpha over 2. So now we can plug in these given values into this formulation for E. So let's see, this will give us that E is equal to 1.96 times 1.3, which is sigma, divided by the square root of the sample size, 40, and I'm going to calculate this off screen with my calculator, and let's see what we get. Okay, so my calculator gave me 0.4028, but I'll just round this to 0.4, and what this tells me actually is that our mean is within this error from the sample mean, which was 12. So really, the mean mu, population mean mu, can be written as x bar plus or minus the margin of error E. So in this problem in particular, we have 12 plus or minus 0.4. So if you wanted to actually do the calculation, then you basically get the following. You get that the mean is in between 12 minus 0.4, which is going to be 11.6, and 12 plus 0.4, which is 12.4. So this is essentially our answer. If you wanted to write it in interval notation, hence the phrase confidence interval, then you can write it as this, 11.6 comma 12.4 surrounded by brackets. This is another way of writing this. So essentially we're saying that the mean is in between these two values. In other words, we're 95% confident that the population mean of weights of kittens in that region is in between these two values, given our sample of 40 kittens. Awesome. So now we'll be taking a look at something a little different that we'll have to do with when we don't have sigma given, and it's going to be a little involved and not too intense, but it's going to be a little involved. So let's take a look at that right now, and then after that we'll take a look at one example, kind of like we saw this example from the previous idea. Right, so now on to the next idea. If sigma is unknown, but S, the sample standard deviation, is known, then we can estimate the population mean mu by this. X bar plus or minus this new error, which is t sub alpha over 2 times the standard deviation over radical n. So this is our E now. Now, something that I must point out, and this is kind of a little new to me, but I'm used to this where we have radical n, and most books, if not all books, use this, but I have, in rare instances, kind of more recently, seen that sometimes n minus 1 instead is used when t is being used. So let me just say, or n minus 1. So you may see that, and if you kind of check your answer with the book, just kind of depending, then you may use n minus 1 instead of n. So if you're not quite getting what the book is getting, maybe change that to this. I'll be using this one for the example we'll be seeing afterwards though, but I just wanted to point that out. Now the requirements to use this are the exact same for the from the previous one, the previous estimate. Only in this case, I don't think we actually need the sample size to be bigger than 30, but we definitely do need it to come from a normal distribution, the sample to come from a normal population, in other words, and we also need the sample to be random. But again, these requirements will be given or else we can't continue with the problem. Now, this t sub alpha over 2 may be throwing us off a bit because we haven't seen that before, maybe. So here I say where plus or minus t sub alpha over 2 are the critical values of the confidence level on the standard student's t distribution curve. Now we're used to the standard normal curve, not the t distribution or student's t distribution curve. Now it's the same exact principle as the z curve, the normal standard normal curve. The only difference is that you can have variations of the curve depending on what are called degrees of freedom, which we'll use df. Now degrees of freedom will depend on what our curve looks like, but for our cases, just because it's kind of hard to draw an accurate picture, I'll just be drawing what will look like a normal curve, but it'll really represent this kind of specific variation of that. And for t specifically, the degrees of freedom are n-1. Now I say that because degrees of freedom actually come up a lot in statistics, and depending on the distribution we're using or the test we're using, the degrees of freedom may vary and may not be the sample size -1, but in this case it is. Okay, and that's kind of all I'm going to say. I guess something else I can say is that as the degrees of freedom tend towards infinity, then this will look more and more like the actual normal z-curve. So the higher degrees of freedom, in other words, the higher your sample, the more normal this becomes. Great. So now, how do we find these t sub alpha over 2's? So again, this is t sub alpha over 2, and this would then be negative t sub alpha over 2, and the mean here is still 0 with the standard deviation 1 because that is from the standard t curve, kind of like for the standard z curve, you have the same scenario. Now how you find these is a little difficult depending on your calculator. Your calculator may have what I'm about to show you or it may not. Now, what we want to use, kind of similar to inverse norm, is what is called inverse t. Now, some calculators have inverse t, some don't. Mine, for example, does not, but there are some ways around this sometimes. Now, inverse t is very much like inverse norm, it just takes the area to the left. So if you type in this of 1 minus alpha over 2, which is the same as 1 plus the confidence level divided by 2, then you'll get the actual t values, the critical t values, that is. If you don't have this, then there are ways to download onto your calculator if you have a TA83 or lower, TA83 plus or lower. Basically, if you have a TA83 or TA83 plus, then you have to, there's a way to download a program which is called critical t. Now, I don't want to discuss too much of how I'm going to find my t values. I'll explain it a little bit, but I won't actually show it with the calculator how I'm getting this. But essentially what we want is we want the area to the right of this to be alpha over 2 and the area to the left of this to be alpha over 2. So essentially we want to use the fact that TCDF, kind of like normal CDF, which my calculator does have, so that's the kind of funny thing. Calculators normally have the CDF or PDF functions, but not normally the inverse functions. So this is why, well, this scenario or this topic is a little hard to talk about. But anyways, for TCDF, again, it's kind of the same thing. For normal CDF, you go from lower to upper or lower to higher. And in this case, we want to go from t sub alpha over 2, our critical value, to infinity. And this should give us our right area, alpha over 2. And that's what I'll be doing basically. I'll be inputting guesses from in TCDF from my guess to infinity, and hopefully getting something that's very close to whatever alpha over 2 is, and then from there I'll actually use that value with my calculation. So that doesn't sound too bad. Oh, also, by the way, for TCDF we need to input the degrees of freedom. So there's actually one more entry here, and that's our degrees of freedom, which again is one less than the sample size. And this will give us hopefully alpha over 2. So we'll take a look at one example of this, and that'll be the end for the video. All right, so now for this example, we're given a random sample of cars that are tested for battery health in a certain facility. And it says that the results are given below. So we actually have the values at this time, not just the sample mean like the previous problem gave us. And we're asked to estimate the mean battery health of all cars in this facility, where the sample came from where the sample was taken, with a 90% confidence level. So now Yeah, so how do we proceed now? Well, let's recall what we need. So we're given that E, our margin of error, is T sub alpha over 2 times S now, not sigma, over radical N. Now S, we actually need to calculate using our calculator. I'm going to use 1var stats on my calculator once I input this into a list, and that'll just give me the standard deviation of that sample. We also need to find X bar as well. So X bar and S, I'll use my calculator to actually evaluate what those are. So I'll do that off screen in a moment. And again, I'm using a 1var stats here in my calculator. Okay. But now for N and for T sub alpha over 2, I can kind of talk about that right now. So N is just the sample size, and you can see there's 6 values up top, 6 values below, so that's actually 12. So here from what we see, the size of the sample is 12, so we know N is equal to 12. Moreover, our degrees of freedom then must be 11 because that's 1 less than 12. Perfect. So we know that, well, we'll discuss T sub alpha over 2 in a moment. S we'll find out using our calculator, and N we now know is 12. Now T sub alpha over 2 I've actually already calculated with my calculator. And again, the way I did that is I used TCDF from a guess to infinity. You can just type in a bunch of 9s or 10 to the 99. I use 3 9s, that's sufficient for a standard curve where your mean is 0 and your standard deviation is 1. And remember, the third entry is your degrees of freedom, which in this case was 11. Now I typed in 1.95 and that was too low. We want the value here to be alpha over 2, which in this case is 0.05. And I can tell that again because this is our confidence level CL. So if CL is 0.9, which is 90%, this implies alpha is 0.1, and that implies that alpha over 2 is then 0.05. So that's what we want our resulting TCDF value to be, because it's the area to the right under this standard T curve with degrees of freedom 11. Okay, so we want this area to the right of this curve, or this particular T value, critical value, to be 0.05. Again, that's half of the significance level, 0.10. Good. And I typed in, just to guess, I guess 1.96, taken from the previous example we got, or we saw, where we got a Z value to be 1.96 for 95. So I just guessed something, and I got that it was too low, that it was about 0.3, meaning that if it was 0.3, that means it's actually further along the line than we wanted it to be. So I guessed lower, and eventually I got 1.80 actually worked. So 1.80 gives you about 0.05 if you type TCDF from 1.80 to a very, very large number, comma 11 for your degrees of freedom. Now, that means the T sub alpha over 2 part is taken care of. That's about 1.80. Perfect. S and X bar, I'll calculate off screen right now using 1var stats. All right, so using 1var stats in my calculator, I got that X bar was 77%. And S, the sample standard deviation, was about 11.31 if you round to 2 decimal places, which I'll do. And again, this is from 1var stats. Perfect. So now we know S, so I'll plug that in here. That was the numerator after all in our formulation for E. And X bar, again, was 77. Perfect. So now all we need to do is calculate what this is, and then write mu to be plus or minus, well, 77 plus or minus this error value. So let's do that and see what we get. All right, so using my calculator, I got this to be about 3.22. And then this implies that the mean is X bar plus or minus this error of estimate, this margin of error. And then again, if we do the plus, so just to write it out completely, we get 77 plus or minus 3.22, which gives us an interval of 77 minus 3.22 gives us 73.78. And then 77 plus 3.22 would then be 80.22. Perfect. So this is it. This is our estimate of the population mean. So that is, we are 90% confident, given this random sample in the facility of battery health, that the population mean, so the mean battery health of all cars in that facility, again given this sample, is in between these two values. And we're 90% confident that that is indeed the case. Now, that really ends it actually. So that ends this example and then ends the video. But one afterthought I kind of want to say, one thing I would like to say to conclude this, is that the more confident we are, the more spread out these values ought to be. And that makes sense, because we can be 100% that the mean is going to be somewhere between negative infinity and infinity. I mean, it sounds ridiculous, but it's certainly true. And you can try to do this problem again, but pick a different confidence level. So if you wanted to change your confidence level to be higher, then you'll get two values that are further apart from the sample mean. Similarly, if you were to pick something with a lower confidence, then the values will then be closer. So that's the last thing I wanted to say then, and that again concludes this discussion on confidence intervals. Really hope you all enjoyed this. So I'll see you in the next video. Thanks for watching, and I'll see you then.